All right, let's dive into a really fascinating puzzle that gets to the very heart of modern AI. We've all seen these large language models do some incredible things, especially when it comes to writing computer code. But there's this weird inconsistency, this paradox, that reveals something incredibly deep about how these machines actually, well, think.
And this is the central question for us today. Why is it that an AI that can write elegant, complex software seems to just fall apart when it comes to formal mathematics? I mean, on the surface, coding and proving a theorem feel like they should use the same logical muscles, right? But as we're about to see, for an AI, they are two completely different universes.
And the difference in performance is, it's not even close. It's a chasm. With code generation, these models are getting an A+. They're writing programs, they're fixing bugs, they're even optimizing code. But when you ask them to build a formal mathematical proof, something that needs absolute step-by-step logical perfection, their performance becomes incredibly fragile. They don't just struggle, they often fail completely. So, to get to the bottom of this mystery, we first have to understand something really crucial. The word math isn't just one thing. For an AI, it's actually two totally separate worlds, each with its own language and its own set of rules.
Okay, first up, you've got the informal math. This is the stuff we all learn in school. Think about the proofs you find in a textbook. They're written in plain English, mixed with symbols. They're basically a persuasive argument, like a story, designed to convince another human being that something is true. They can even skip a few steps because they assume the reader is smart enough to fill in the blanks.
And then you have this other world, formal mathematics. This is a whole different beast. This is a purely symbolic language, kind of like a computer program for pure logic. Every single step has to follow a super rigid, explicit set of rules. A machine can check it. And there is zero room for ambiguity, no intuition, no hand-waving. It is absolute mechanical precision. And that difference between a persuasive story and a perfectly executed computer program, that leads us right to the core of the paradox. See, it all comes down to how these two worlds handle mistakes. Think of it this way. It's a great analogy. Writing code is kind of like hiking a trail. If you take a wrong turn, you introduce a bug, you can usually backtrack, fix it, and get back on the path pretty easily. Your program might even work partially, giving you clues about what's wrong. But a formal proof? That's like walking a tightrope. One tiny slip, one single logical misstep, and the whole thing comes crashing down. It's all or nothing. The paper we're drawing from for this explainer puts it perfectly. In the world of formal proofs, the environment is just incredibly unforgiving. Unlike code where a program can be, say, 99% correct and still be useful, a proof is either 100% valid or it's completely worthless. Let's just walk through the coding process for a second. The AI generates some code. A test suite runs it, and then it gets this really rich partial feedback, maybe 9 out of 10 tests passed. Wow, that feedback is gold. It tells the model pretty much exactly where the problem is, which lets it make these small, focused fixes. The path to getting it right is, well, it's pretty smooth. But in formal proof, the feedback is basically just a yes or a no, a pass or fail. The proof checker just says, nope, that's wrong, without giving any useful clues about where the logic went off the rails or how to fix it. This brutal, all-or-nothing feedback makes it incredibly hard for an AI to actually learn from its mistakes. And to make matters even worse, there's this massive data gap. Code models are trained on literally billions and billions of lines of code scraped from all over the internet. But the amount of training data available for formal proofs, it's orders of magnitude smaller. We're talking a mountain of code data versus just a tiny hill of formal proofs. There are way fewer examples to learn from. So this failure in formal math isn't just some quirky little problem. It's actually a window into something fundamental about how these AI models understand any kind of structured reasoning at all. It really forces us to ask this deep question. When an AI writes code, does it actually have an internal model of what's happening? Does it understand the state of the program? The values of variables, the flow of logic? Or is it just an incredibly sophisticated mimic predicting what word should come next based on all the patterns it's ever seen? And the evidence really points to the latter. You hear this term stochastic parrots a lot. For coding, that means the AI isn't really simulating the program in its mind. Instead, it's a master of pattern recognition. It predicts the next piece of code simply because it looks statistically similar to the countless examples of loops, functions, and variables it was trained on. And that right there,
That is the heart of the paradox. This superficial mastery, this brilliant ability to just mimic patterns, is good enough for the forgiving world of coding where you can make mistakes and recover. But that exact same strategy completely shatters the moment it runs into the brittle, unforgiving, all-or-nothing world of a formal proof.
The researchers behind this have this incredible line, and it's fascinating, maybe even a little scary. They say the training in AI on informal human-style math teaches it to reason with intuition and narrative, to think like a mathematician. But training it on these rigid, formal systems just teaches it to execute mechanical steps, to think like a prover. It seems like two totally different kinds of intelligence are starting to emerge.
So where do we go from here? Is this just a dead end? Well, not so fast. Researchers are all over this problem, and they're already coming up with some really clever ways to help AI bridge these two worlds. And the future here is really interesting. It might not be about forcing AIs to get better at these rigid, machine-like tactics. Instead, the whole approach is shifting. People are looking at proofs that read more like human arguments. They're teaching models to reason both forwards from what they know and backwards from the goal they're trying to reach, just like we do. But at the end of the day, this isn't just about making AI better at math. It leaves us with this huge question to chew on. As we work so hard to teach these machines to reason in more human-like ways, we have to wonder, in the process of building these new minds, how are they in turn going to start shaping our own?